Okay, I'd like to tell you about Faraday's Law, the basics. This will be part one. And so before I get into Faraday's Law, however, I just want to show you that with electricity and magnetism, you can cause a current that's going, you can cause a wire that has a current in it to move up or down, and that's called the motor effect. Or you can take and move this up and down and get current. And so that's kind of what Faraday's law is about. By moving the magnetic field in relationship to the wire, you can get a current in the wire. Okay, well, let's just look a little bit further into this. If current's going this way down the wire in this magnetic field, remember the magnetic field goes from north to south, because if I put a compass here, the north pole would be attracted to the south pole. So if the field's going that way, I take my right hand and I put my thumb in the direction of the current, and so this is going to be pushed down. So this wire will be pushed down. That's the motor effect. We're taking electricity and we're making mechanical energy. We're making kinetic energy. And so, but you can do the opposite. You can take mechanical energy, and by forcing this wire down, you can get the current to flow in it. And so if I push this wire down, that would be electrons that would be moving down. Now if electrons, take my left hand, if electrons are moving down, put my thumb down, and the field is going that way, then I'm thinking the electrons will get pushed down the wire that way. Are you? Now the electrons going down the wire that way means that the flow of conventional current would be this way. Okay, so we took electrical energy and we made it mechanical energy. It forced the wire down. And this way we took mechanical energy and we made electrical energy. And that's kind of what Faraday's law is about. It's about taking and making some, you can take in mechanical energy if you need to and make it into electrical. Okay, so Faraday's law. I'm going to do a rear demo here. But before I can do the rare demo, I need to show you just how a galvanometer works, because I have a galvanometer in my demo. Okay, so this is a galvanometer right here. You see that I have it hooked up to a coil of wire, a solenoid, and this wire, or this galvanometer, has a needle. You can hardly see it; it's very fine, but it can indicate the flow of current. And the way it does that is pretty simple. All it does is, if you have a coil of wire, or just a loop of wire like this, and let's say the wire is on an axis, so the orange line is an axis, and I'm going to go ahead and attach a needle to this. That's the needle I just showed you. And now this can pivot around like this, back and forth. Now, if I pass current through this, let's say the current comes down like this, like that, and this way, and then that way. And if I put this in a magnetic field, so I'm going to put in a uniform magnetic field right here. Try to. That's B. Then using the right hand rule, if current's going that way, and the field's that way, this part is going to be pushed down. So this will have a force down on it. And this end right here will be pushed up. So that puts a torque on that wire. And what they do then is they attach to the axis a little spring that doesn't allow this to move very much. When it torques, the spring tries to pull it back, and so the needle just gets this equilibrium spot where there's the same amount of torque being applied by the coil is equal to the torque being applied by the magnetic force. And so you know how much current is in that galvanometer. You know how much current is in there by how much the needle deflects. Okay, well, the point here is that I'm going to get this needle to deflect without a battery. So I just have a coil of wire, and I have a galvanometer and some wires, and I'm going to take a magnet, and as long as I move the magnet relative to the wire, then I'm going to get a current to flow in there. So watch. I don't know if you can see that very well, but the current is flowing in there. Notice that just having the magnet by the wire doesn't do it. You need a relative movement there to get that to happen. Okay, so that is just a demonstration on Faraday's law. And now I want you to see something here. Let's go and take a look at Faraday's law. Okay, this is Faraday's law. It says that the E induced around a loop of wire will equal to how fast the flux changes in the hoop. Okay, so this flux, this is not just any old flux. This is the flux that's changing in the hoop. So the EMF that's induced around a hoop of wire is equal to just the rate at which the flux is made to change in that hoop of wire. Excuse me. So the derivative of phi with respect to t is just describing how fast flux is changing with time. Now, just as with instantaneous velocity, say in the x direction was dx dt, and average velocity in the x direction is delta x over delta t. The same thing is true of induced voltage. If you want to get the average, then you're just going to take a delta phi over delta t. Now, this negative sign I'm going to explain in another video with Lenz's law. I'll show you what happens with that negative sign. But let me just show you an application, or just one very simple problem with Faraday's law. So it's all about how fast that flux changes with time. Okay, so imagine we have this hoop of wire, and this just, say, copper wire, 10 centimeters, 10 centimeters, 10 centimeters, 10 centimeters. And the magnetic field in here is 2 Teslas. And at time t equals 0, it's 2 Teslas. Now, it's straight out of the paper, straight out at us. So B and dA, let me draw you a little dA. There's a dA. They're in the same direction. Okay. Time 0.01 seconds later, there is no field in the wire. So we've just changed the magnetic flux. There is flux, there's no flux. The rate at which that occurs will tell you how much EMF will be induced in this wire. By the way, if you induce EMF in the wire, you'll induce a current in the wire. Okay, so to show you how to figure out just how much EMF is induced in the wire, I write down, let's find the average EMF induced. It's going to be equal to the negative delta phi over delta t. So that's a negative. And for delta phi, I'm gonna do the initial flux, or the final flux. The final flux is 0. So there's no flux in here. Flux is Teslas times meters squared, or Webers. Excuse me. And then the initial flux, I could do the integral of B dot dA, but you see how B is uniform throughout here? And the dA is in the same direction as B. So that just goes to B times A. So if I did the integral of B dot dA, that just goes to B times A, because B is uniform and dA and B are in the same direction. So that's going to be 2 Teslas times, the area is 0.1 meters times 0.1 meters. So it's going to be 0.02 Teslas square meters. And the time it took was 0.01 seconds. So how much EMF will I have induced in this hoop? Let's see. This negative will cancel that negative, and so I'll just be left with 2 volts. Apparently, that gives us volts, and maybe we'll show you how that works in another video. But that's just the basics. If you change the magnetic flux in a wire, you're going to induce current, and that's the basics of Faraday's law. There's more on the basics in the next video, though. Don't miss the next video.